By now, you've done your atomic model project and you have an idea of the evolution of the atomic model. How it first started out with something very simple with Dalton's atomic model, and it progressed to something a lot more complicated with Chadwick's simplified atomic model. So in this section, we're going to be learning about 4 of the 5 atomic models. So we're first going to look at Dalton's model, and you're going to remember that Dalton's model is these solid structures. Now, in the textbook, we use balls, but that can be any kind of structure, really, where one particular size of structure, let's say solid sphere, is equal to one type of element. So in the case of, let's say, H2O, if you've got 2 hydrogens and 1 oxygen, well, Dalton's model would express this as having, if we used, let's say, spheres, if hydrogen sphere was a solid black sphere, and let's say oxygen was a larger red sphere because it is a bigger atom, if we wanted to represent a molecule of H2O, we would represent it by combining the proper ratio of hydrogens and oxygen. It would give us something like we have on the right of these letters. Now, Dalton's model is very simplistic. It assumes that the atom is going to be one solid, indivisible ball. And this idea of this solid sphere stays with science for a very, very long time. And it's not until Thomson comes up with some experiments that we start to kind of improve upon the idea of this solid structure. So Thomson's idea takes Dalton's solid ball or spherical structure of the atom, and it improves upon it, saying that, wait a minute, it's not just an atom is not just one substance. Okay, yes, the atom is still considered to be the smallest, most indivisible substance by many, but in reality, what you have here is you now have this substance, okay, this structure, this solid spherical structure that now has different particles within it. Thomson's idea, okay, builds on Dalton's model because here we have the actual, solid structure, which is the portion in white, and this is considered to be, this overall positive substance. Okay, it's a solid positive substance, and these little blue electrons, well, we coined them electrons later, but these little negative charges are stuck. Okay, so it is a negatively charged particle, and it's stuck or embedded in the surface of this solid structure. And Thomson comes to these conclusions by undertaking several experiments with cathode rays. So we're going to look, the next page is going to look at the cathode ray experiment on page 8 and 9 of your text. And we're going to try to shed some light on what exactly happened in that experiment. So here we have an example of a cathode ray tube. Okay, it's a really bad drawing, I'm sorry, but I'm just going to explain to you what's going on here. Okay, so this small disc at the back, right here, is known as the cathode. Okay, and the cathode, when all the air is, the vast majority of the air is evacuated out of this glass tube, this sealed structure, so the gray is the glass tube, Okay? When all of the air is evacuated, or the vast majority of it is evacuated out of this glass tube with the help of a pump, we turn on the power supply down here, and it's going to send large amounts of voltage. So a huge electrical current through these two plates. This second plate here is known as the anode. And what ends up happening is that it was measured that when there's a high voltage that goes through the actual cathode, it starts to emit these little particles that end up being attracted towards the positive anode from the cathode. If we did not have an anode here, these little particles would actually just stick around the cathode. Like they would just kind of be like, just be stuck here. Okay? But because the anode is basically the opposite of negative, it's got a positive charge to it, okay? And the cathode has a negative charge, opposites attract. So these particles get directed towards and through the actual anode, and in the old school television sets, they would hit these phosphorus-coated screens, which would then turn them into little, I won't say pixels, but something very similar. Okay, so what ends up happening here is because these little unknown particles get attracted to negative or positive anodes, we know that opposites attract. So Thomson deduces that these little particles are actually negatively charged. And he gives them, I'm not sure if it was him, but that's where the concept of the electron comes in. So when we look at our blueberry muffin, this is what Thomson is alluding to when he says that, okay, this substance here is still going to be considered this positive sort of, base, all of this stuff in here. So the batter of your muffin is still all going to be positive, but every once in a while we will have these negatives, these little negative charges, and because opposites attract, the negatives are kind of sticking to the outer surface of this solid sphere. Okay? So that is kind of where Thomson is coming from. Now, if we go back to this rudimentary drawing, we'll see that Thomson proves that these little particles have a negative charge by actually throwing a positively charged substance near them. So if something had a positive charge and it was brought near, this actual ray, well, the ray would actually divert down and be attracted towards this positive substance as this positive substance was brought closer. The same thing happened when a negative substance was actually brought closer. Okay, when a negative substance came in and a negative substance was brought closer to it, it deviated away from, this cathode ray deviated away from the negatively charged substance. So that kind of proves the idea that opposites attract. So if that is the case, if opposites do in fact attract, and we see this here where the actual the little particles here, the negatively charged particles are attracted towards this positively charged anode, and they actually pass through the center of it, and they continue on their journey. Well, we can say that because opposites attract, the cathode must then be emitting negative particles. And this is where the idea of this negatively charged electron comes from. So if we look at pages 10 and 11 of our text, we see that, as technology advances, as power supplies get stronger, okay, and our equipment gets better, that we're able to carry out more and more experiments to try and discover what is going on with this little structure known as the atom. All right, and it's in the late 19th century, early 20th century that J.J. Thomson conducts all of these experiments with cathode ray tubes. And if you have a look on pages 10 and 11 of your text, and you should have already gone over this because of your project, you'll see that at the top of page 11, we have the illustration of a cathode ray tube. So here is a slight recreation of figure 1.8 on page 11 of your text. This is one of Thomson's experiments, where we have the cathode here, okay, in this glass tube, and we have the anode. And we know that this is attached to power supply 1, and there's a second power supply in this experiment, power supply 2. So, what ends up happening here, when the power supply is turned on, voltage is sent through this to this cathode, and it's also sent through to the anode. And it creates all of these electric particles that get attracted towards the anode. So the anode forces them to go in this actual direction. Because remember, if there was no anode there, they'd all hang out where the cathode is. And the second power supply is actually charging two metal plates within the glass tube. Now, if we know that cathode rays are negatively charged, where do you think they're going to be attracted to? These lines are going to deviate closer to the actual positive and the positive plate here, because opposites attract. They're going to want to stay away from the actual negative plate because similar charges repel. And this is a classic example of Thomson's model.